Now we're going to talk about this major topic, the fundamental theorem of algebra, okay? And I've been alluding to it all along, but we need to clarify some things moving forward, okay? So we're going to say when we have a polynomial equation of this sort, descending powers, all right? Of course, polynomial implying that all these powers are integers, okay? And that all these coefficients are real numbers. We're going to say, okay, that the power, the highest power, okay, which typically is listed first, but does not always have to be, okay, but the highest power in a polynomial will tell you the number of solutions, the maximum number of solutions. But for clarification, we have to say the maximum number of complex solutions, okay, which is inclusive of real and imaginary solutions. So, long and short, you know, if your expression here is a fourth power expression, then it can have at most 4 complex solutions. In fact, we should say it has exactly 4 complex solutions. Okay? If it's a fifth power, it has exactly 5 complex solutions in some combination of real and imaginary. A third power polynomial, known as a cubic, would have exactly 3 complex solutions. And a quadratic, a second power, would have exactly 2 complex solutions. And we'll find that either they are, either they are imaginary or real for this quadratic. There's the expressions, just examples of the expressions, okay? All right. Now, okay, complex solutions, as we said, can be real solutions and or imaginary solutions. So again, this polynomial of degree n must have a certain number of real solutions and a certain number of imaginary solutions such that their sum is always equal to this power. And furthermore, any imaginary solutions, okay, will be in pairs. Furthermore, they will be in what we call conjugate pairs, okay, as stated down here, okay? So if you are told that one of your solutions is a plus bi, you automatically know the other is a minus bi, where of course I is the imaginary number, square root -1. A and b are real numbers of this complex, what we call complex conjugates, as listed here, okay? So let's talk about actual polynomials. Quadratic here. As we know, a quadratic will have 2 solutions, 2 complex solutions. But, okay, since the imaginaries are in pairs, and it must have 2 total solutions, either it has 2 imaginaries or 2 reals. So we say here, okay, we either have 2 imaginary solutions and 0 reals, or 0 imaginary solutions and 2 reals. Now, of course, I've been trying to condition you that from, sorry about that, but from conditioning you from first look, try to factor it. It does, in fact, factor. And when it does factor, it reveals us the solutions, which are real, which is coincident with, okay, not coincident with the picture showing the 2 intercepts, okay? Now, actually, that's the picture for this guy, nonetheless, okay? The picture of this guy would have 2 intercepts. Now, we look at this one, okay? This is another quadratic, a factorable quadratic, if you will, okay? In fact, it factors with 2 factors which are identical, okay? So they are real. And again, since we were mandated that we can only have two solutions and that imaginaries can only come in pairs, we must conclude that these two solutions are the same, okay? And there is but no imaginary solutions, only the real solutions. But since they are the same, we refer to that as a multiplicity, meaning, okay, a double, in some cases, maybe a triple or quadruple solution, which is the same. We should see more of those moving forward, okay? Okay. Now, we look at this quadratic. We say, well, it doesn't factor. Okay, so if it doesn't factor, we always have the quadratic formula to determine if we can find this solution. And of course, quadratic formula, first order business, should be to check the discriminant. We just went full blown here with the quadratic formula. And of course, that reveals the discriminant is negative, which means that the discriminant negative means there's no real solutions. And since there's no real solutions, and this thing must have a total of two complex solutions, we conclude that the two complex solutions are, in fact, imaginary. And they are, as indicated here, -1 plus I root 3 over 2 and -1 minus I root 3 over 2. Actually written as a complex number, we probably should say -1/2 plus 1/2 I root 3, -1/2 minus 1/2 I root 3. Now, and of course the implications here graphically is that this has no x-intercepts, no zeros, no real solutions, okay? So they are all implying the same thing. Real solutions, okay, imply that you have x-intercepts. X-intercepts are analogous for what we coin as zeros of the function, which we have yet to define, but the function would be what determines the graph, okay? Here again, we look at now a cubic expression. The cubic expression would have three complex solutions. Owing to the fact that if there are imaginary solutions, they would have to come in pairs. So we might say, well, if we had imaginary solutions, there would have to be two of them, leaving us with one real solution. Otherwise, we'd have to have three real solutions. So the picture shows us that there is only one intercept, therefore implying that there is only one real solutions. There are three overall complex solutions, one real, leaving us with two imaginary, okay? Let us look at this expression, okay? All right, let us look at this expression, I'm sorry. Moving backwards. Looking at this expression, it is a fourth power polynomial. Four complex solutions. How could we come up with them? Well, we could have two real and two imaginary. Okay, again, owing to the fact that imaginary must come in pairs, okay? We could have four imaginary, in which case we'd have to have zero reals. Or we could have four real solutions and no imaginary solutions, okay? Let's see if we can find some of these solutions, okay? We've been learning how to factor these expressions and do find that it is factorable. This expression factorable to x squared minus 1, x squared plus 3. X squared minus 1 subsequently factors as a difference of squares, x plus 1, x minus 1, revealing us our two real solutions. x squared plus 3 has no real solutions when set equal to 0. It has imaginary solutions, okay? So the 4 solutions to this expression, to this equation, 2 reals, 1 and -1, and 2 imaginary, okay? I root 3 positive, I root 3 negative. Perhaps you'd want to try to find the solutions to this 9th power expression. You ask yourself, okay, how many solutions could it have? Well, how many complex solutions? We know exactly 9. What kind of combinations would they come in? Okay, there's the question that I'm leaving for you to answer. What kind of solutions would this have? What pairs, okay, of conjugates and of imaginaries and or reals might this thing have? You should be able to factor this, so I'm going to leave that one for you to try to explore and factor, okay? We'll terminate the video with this and resume with another video.